last lecture. Okay, just to catch up everything. So we studied the reverse bias condition of the diode or the junction. Okay, and we said that the most useful application for reverse bias is what's called Varactor Diode. Okay, which is just a variable capacitor, and this is actually its symbol. So just like any diode, but we added another bar here. So this is the original symbol of the diode, and we just add another bar just to say that this diode will act as a capacitor. Okay, voltage controlled capacitor. One thing I missed in last lecture is the units of this CJ. So we took this this equation, and we also calculated, and we took another equation for CG node, the junction capacitance at 0 voltage when there is no reverse bias. Okay, but the dimensions of this parameters is actually farad per meter squared. It's not per unit area. It's not farad. So usually we take capacitance as a farad, but here, because you know everything, every characteristic in or all the characteristic, for most of them, of the diode or the junction depends on the geometry, in particular the cross-section area, so that we normalize everything to the cross-section area. Okay, so the dimensions of this parameter CJ is actually farad per meter squared. So that in the homework that I published, the area is important because you cannot complete the or solve it correctly this homework without considering the area. Okay. We also studied the diode or the junction in forward bias condition, in which I connect the positive terminal of the battery or the source to the B side of the junction, and the negative terminal of the battery to the N side of the junction. Opposite to the reverse. In reverse, we connect the negative to B and positive to N. Okay, and you know we showed you the relation between ID and I node, which was originally, you know, reduced or derived for forward bias, but we discover afterwards that it's also valid for reverse bias. Okay, because in reverse bias, you remember here I node. Okay, this constant in here in this relation, we said that I node carries in it all the characteristics of the diode or the junction, the area, the doping, the material, you know, the temperature, and it's also can be called saturation reverse current, because when you have VD in reverse, I mean VD is negative, and it's much larger than VT in reverse bias condition. If we apply this relation, we find that ID is equal to minus I node. So this relation, although it was derived for forward, it can be applied in both. Okay. We also get to an important observation, is that in forward, the change of I versus V is rapid, is very rapid, it's very high, it's exponential. Okay. And we, you know, we conclude this in this sentence, that ID is increasing with VD, and the rate of increasing is increasing as well. The slope is increasing. The opposite is VD. VD is, you know, also increasing with ID. If we draw VD on the vertical axis now, and ID on the horizontal axis, okay, we see that VD is increasing, but the rate of the increase is decreasing. The slope is decreasing. So for example, the slope here is larger than the slope here. That's obvious. Okay? And finally, we said that while the diode is on, and we see also this last lab, VD, the voltage drop on the diode, is usually approximately equal to VBI or around VBI. Okay. Okay, that was a recap of the last lecture. It was a very rich lecture. Now let's take some examples. And in this lecture, we will take some difficult example, we can say, or relatively difficult. They are easy, but for other examples, they're relatively difficult. So let's start by this one. Okay, you have here a very, very simple circuit. Very simple circuit. The simplest that you can do. Okay, a diode, a resistor, okay, and a source, a battery. The battery is 2 volt. The resistance is 0.1 ohm. And I naught, which is a characteristic of the diode, is equal to 1 picoampere. And I said I naught usually, or IS is really usually very, very, very small. And the question is simple. Find VD and ID. Before anything, anything, we should point out the directions of ID and VD. Okay, the diode, okay, just like any other element, except the battery has, a voltage in one direction and the current in the opposite direction. So the current of the diode flows from B to N in that way. So ID flows in that way. And the voltage is from N to P, opposite to the current. This is very important. Okay, very, very important. So let's solve this. Okay, so we have 2 unknowns. So to solve it, we need 2 equations. That's very easy. So the first equation is actually KVL, Kirchhoff voltage law, which says that if you have a current like this, okay, which is ID, goes through a resistor, so you have here a VR, and this is the direction of V input, and this is VD. So V input equal to VR plus VD. If anybody has some confusion with KVL, just let me know. That's very fine. Okay. We can say it's in another way. We can say V input minus VR minus VD equal to 0. So I just move the VR and VD to the other side and become positive. Good, but VR is actually equal to ID multiplied by R, because R and the diode are in series. So the current that flows through the diode is actually the same as the current that flows through the resistor, plus VD. The input is known to us. It's a 2 voltage. It's 2 volt. And ID is unknown. R is known. And VD is unknown. So we have here equation 1 and 2 unknowns. We need another equation now. So let's see. We know for sure that ID equal to I naught exponential VD over VT minus 1 equal. I know is 1 pico. You can write it in that way, that's fine. Exponential VD, and VT is 26 millivolt minus 1. That's another equation. Also in 2 unknowns, the same unknowns. Here, VD and ID are the unknowns. And here is also VD and ID are the unknowns. Now I'll give you 2 minutes. So we have 2 equations. We have 2 unknowns. So I'll give you 2 minutes, because we have 2 unknowns, okay, to solve it. Okay? Just let me know after you finish, if you finish. Anybody reached anything? Any conclusions? If we can solve it easily or not even?
You can get VD. It's just trying to get VD out of that exponential. It's a little challenging.
Yes, because they are not linear. So you have one equation which is linear, equation 1, That's good. But the other equation is not linear. So any trial to make it, in the conventional way to solve the equations, it will be failure. You cannot, separate ID in one side and everything else in the other side. You cannot do that with nonlinear equations like this. That's why it's really hard to solve, okay? Because you cannot have one unknown in one side and all other, known variables or known parameters on the other side, okay? That's why you cannot do that, okay? So those are equation 1 and 2 are, or not, let's say more precisely, equation 2 is nonlinear. So we cannot solve equation 1 and 2 with the conventional way. Okay, and let's try it. Let's give it a try. Let's see. So here, for example, if you just take ID, you know ID. Okay, so let's substitute in equation 1 with this value. So 2 equal to ID, which is I naught exponential VD over VT minus 1 plus VD. Okay, so we need VD in one side and every other known parameter on the other side. Okay, yes, you have one equation with only VD. That's good, but you cannot separate VD in one side and try it for 100 years. I'm sure you will not reach anything. Okay, so we cannot. Let's put this observation here. We cannot separate VD in one side and all other known parameters in another side. That's why we cannot solve it linearly, only with the conventional way. Okay, so we need, this is the conclusion, we need some iterative solution, for example. You guys have taken before something like Newton-Raphson method or something like this. All these, or graphical method, for example, to solve the equations. Okay. So there are some methods that can, solve approximately. Okay. Two equations together, two nonlinear equations together. Okay. So one of them, which will be clear for you, is to solve them graphically. Okay. We can, or graphically, etc. In many ways, but all of them need a computer, for example. Okay. So, for example, in graphic solution for this, you're gonna draw the two equations. Okay, and the intersection of the two equations is the only points, okay, the only values for VD and the ID that satisfy both equations at the same time. So let's what are the equations that we have? So we have this equation here. So let's make it in another way. So from 1, we have ID equal to 2 minus VD over 0.1, or in other words, 20 minus 10 VD. Okay? And from 2, it's easy. From 2, let's go back to green. From 2, that's very simple. ID, it's obvious there. ID equal to 10 to the minus 12 exponential VD over 0.026 minus 1. So let's draw this. So what we need two values for VD and ID, and both, and these two values, okay, or this pair, we can say satisfies equation 1 and equation 2 at the same time. That's what we mean by solving two equations together, to get the value that will satisfy equation 1 and also satisfy equation 2. So let's draw them together. Let's go back to our green here. Okay. This is Mr. VD. This is Mr. ID. Let's draw the first equation. So the first equation is very simple. It's just, you know, a linear equation, but with negative slope. Okay. So it's something like this. And at VD equal to 0, ID will be equal to 20. And at ID equal to 0, VD will be equal to 2. That's very simple. The other one is really, you know, you cannot draw it, you know, precisely using just your hand. But we know the shape, it will be something like this. So equation 2, so this is equation 1. So let's draw equation 2. We know equation 2 will be something like this. This is equation 2. Okay? So where is now the point that satisfies both equations? Satisfies me, it lies on the first curve and also the second curve, which is the intersection. So the intersection point here is the one that, you know, satisfies both equations. So this is VD solution. This is the solution for our equations for VD, and this is ID solution. This is solution for VD, and, you know, so the solution should be the intersection. And in that case, just, you know, in symbols, ID should be equal to ID solution, VD should be equal to VD solution. That's it. And of course, it's not that easy to do that by your hand. So I make here a program, a Matlab program. I will share this program with you. It's a very simple one. Okay. So let's see what I have done here. Okay, don't worry about Matlab. The exam will not have a Matlab. I'm just showing you how to do that. Okay. So we have here our first variable. So I put here IS equal to 10 to the power minus 10, like just like the example, and the resistor is 0.1, just like the example. Again, V input or VS, I call it V input here, but here it's called so let's call it VM. I'm very sorry. Let's call it VM. That's fine. Okay, and also we should change it here again. Okay. Not to confuse you. And here ID equal to the X. So Matlab will just, you know, substitute this value VD with this series, which is a series of numbers between 0 and 0.7 with the step 0.1, like 0, 0.1, 0.2, 0.3 until we reach 0.7. Okay? I'm sorry, it's 0, 0.01, 0.02, 0.03 until we reach 0.7. Many numbers. Okay? So here I am plotting the first curve, which is the exponential curve. And then I am plotting the second curve, which is VD equal to V input minus VD over R. Okay, so let's, you know, run this. and get you the graph here. Wow. So look here, we have here our, equation 1, which is linear with negative slope, okay? And here's the second equation, which is exponential. And here is the solution. So let's, approximate it. It's maybe here. It's between these 2 points. So let's say enlarge this. It's, we can say it lies between these 2 points, the intersection. So this point here is 13.3, and the voltage is 0.67. And this point is 13.4, and the voltage is 0.66. So we can say roughly that if we go back to this guy here, we can say roughly that ID solution is equal to 13.35 amperes, and VD is equal to 0.665. It's approximate solution. You cannot get the exact one. It's really difficult. I'm not aware of any method that can give you the exact solution. Okay? Because all these methods that solve nonlinear equations are, approximate solutions. Okay, guys, so we see now that, the conventional way, or the first intuition way to deal with such the new device that we discover, which is called diode, is not really, flexible and, take time to solve it. So we need, some smarter ways, we can say, to deal with it. Okay, so let's take, I will go back to this, to this example again, okay, but next lecture, when we put some, approximations for the diode, so that we can solve this in a better way. Not a better way, it's, it's a faster way, but with reasonable accuracy as well. So let's take another example. And in this new example, we're gonna start to think more smartly, okay, than the previous one. So here we have 2 diodes, okay, VD1 and VD2. These 2 diodes both have the same breakdown voltage. You remember, guys, from the previous lecture, we said that there is something called breakdown. I forgot to mention it in the recap, but this was the last thing that we talked last lecture. We said that in reverse bias, okay, in deep reverse, the current usually equal to minus I naught, the saturation current. But at some point, something called breakdown happened. When you have very large electric field or very large reverse voltage on the junction. Okay, and the diode will start to conduct current in reverse. Okay, so these both diodes have the same breakdown voltage of 100. Okay, but diode 1 has I naught different from I naught of diode 2. So I naught 1 is 1 microamps, and D2 has 2 microamps. Okay, so the question again is very simple. Find ID1, VD1, ID2, VD2. But in 2 conditions, or 2 sources, or 2 inputs. When first V input is equal to 90 volt, and when V input is equal to 110 volt, 110 volt. Okay, so let's do the exact, solutions that we just saw. The myopic one, just, put the equations and try to solve them. So let's do that, that's fine. So we have 4 unknowns here. We have 4 unknowns, which are ID1, VD1, ID2, VD2. Okay, that's good. So let's put down the equations. The first equation is obvious, the equation for diode 1. ID1 equal to I naught 1, and I naught 1 is known, exponential VD1 Vt minus 1. Good. So this is an equation in two unknowns, which ID1 and VD1. I note 1 is known and Vt is just 26 millivolts. ID2 equal to I note 2 exponential Vd2 over Vt minus 1. I'm sorry, minus 1. Another equation in two unknowns. So we have two equations in four unknowns. The third equation is actually the Kirchhoff voltage law. So you have here V input, you have here VD1, you have here VD2. So I can say that V input plus VD1 plus VD2, they are all in the same, they are all clockwise direction, equal to 0. So we have three equations in four unknown, but we need another equation. Anybody have a clue? What should be the fourth equation? We have still another equation, so that we can have a complete set of four equations in four unknowns, and we can solve them and get the accurate, iteratively, and get some accurate estimate for VD1, ID1, VD2, ID2. Anyone can give us a clue where is the fourth equation is? It's very easy. So where is ID1 and ID2? So this is...
It's KVL.
Yes, not KVL, Kirchhoff current law, KCL. Okay, so this is ID2 and this is ID1, right? But they are in series. So actually ID1 is equal to ID2. So name them another name. So for example, I, and that's it. So let's call them I. And assume this I in any direction. Oh, I'm sorry, the same direction. Okay, so this is, from KCL. So we're gonna put this is equal to I. So now this is the two unknowns here is I and the VD1, I again and VD2, and VD1, VD2. What are the number of the unknowns now? They are three unknowns. And we have three equations. Then you can do the graphical solution or Newton-Raphson or iterative solution. There are many ways to do that. Okay. But they need programming and stuff. It's not that easy. So we are not dealing with that again. We don't want to deal with that. We need some approximation, some smartness to solve and get the solution just by paper and hand. So this is equation 1. Okay, you can solve, then you can solve graphically or whatever, etc., to get I, VD1, and VD2. And of course, I is just equal to ID1 and ID2, which is not smart. Now, the other solution, so this is the exact solution. So the other solution, number B here, is, smarter solution. Because it will give you also some accurate result, just like the first one. And I will show you that. So let's go down a little bit here. Or before that. Okay. So let me draw the two, just a sketch for the two characteristics of both diodes. So this is diode 1. VD1, ID1. And it should be something like this. So we know there is a breakdown, and the breakdown happens at VDD. Some voltage called VDD, which is equal to 100. And we know in deep reverse and before the breakdown, the current is saturated at I node 1. That's good. Now let's do the same for Mr. Diode 2. VD2, ID2, and we may have something similar here, but here now it's different. Guys, I am drawing this scale very large, although I know it's very small, just to make it clear for you. But I know it's very small. Okay. And why this is different from this? Because I know 2 is 2 microamps. This is minus I know amp, sorry. And this is minus 1 microamps. Doubled. Okay. But they have the same breakdown voltage. It's also equal to 100 volts. Of course, in reverse, it will be minus 100. Good. So we need to make some. We know the situations or the conditions under which the diode can work. Okay. And we know in certain conditions there will be some certain known or knowns or givens. So for example, if we are sure that the diodes, for both of them, for example, are both in deep reverse, and before breakdown, we know that ID1 will be equal to minus I naught 1. So we know one of the unknowns now. And ID2 will be equal to minus I naught 2, which is minus 2 amps. So 2 of the unknowns are known now for us. Another situation, if you are sure that the diode is working at the breakdown here, I mean, you will be sure that the voltage is equal to minus dBd because it's a reverse, so it's minus. Okay, of course the current will be larger than in magnitude, larger than the I naught of that diode. Okay, so in certain conditions we know some certain information, so we can solve or get the values of some of our unknowns. So first, let's go back to our circuit and see. Let's ask us the question: these two diodes are reverse or forward? Or maybe one of them is reverse or one of them is forward. Just to give me an answer now. Any one of you. Don't be shy, just say. Just make a guess. Yes.
Looks like they're both reversed.
That's right, yes. Both are reversed. How we could know that? Okay, although it's not clear, just like the other one, which you have, one diode connected to one source because we have one diode here. We do it in a similar way. We say that whatever close to the N and whatever close to the B will give us a clue if it's reverse or forward. So here the positive terminal of the input is close to the N of VD1 and also N of VD2. Okay, and the negative terminal of the battery here is closer to the B of either VD2 or VD1. So both looks like reverse. Okay. And remember, now we are doing with with condition. We will assume some condition and prove it right or wrong. If we prove it right, then this is the solution. If we prove it wrong, okay, we will assume another assumption. Because we know the situation at which the diode can work on. Okay. So the first information that we were gonna build upon here now is that the first equation, the first assumption, the first information is that both diodes looks reverse. We will prove that they are really reverse, but since we didn't get any numbers in it, let's call it looks like they are reverse. Okay, good. Another information, for A, you should solve the is a problem for V input equal to 90 volt. Good. So if you're gonna solve it for 90 volts, so let's assume now we are solving number A, in which V input is equal to 90 volt. We should solve it at 90 volt and 110 volt. Let's do first with 90 volt. Basically, if we know now they are reverse, or we assume they are reverse, okay, and this guy now is 90 volt. If any diode is reverse, it may be also a breakdown, right? Because breakdown happens in the reverse bias. So maybe one of them is break, or maybe both of them had breakdown. So if one of them is breakdown, what should be the voltage on that? It should be 100 or minus 100, okay? And from which, so the diode cannot generate its voltage from by itself. It needs another source to make the voltage drop. So if we assume that one of them is breakdown, it needs 100 volt, although our input here is only 90 volt, less than the breakdown. So we have another, clue now is that they are reverse, and 90%, I don't know, they are not also breakdown, because input voltage cannot afford 100 in order to switch any of them into a breakdown. Okay, so since V input is less than 100, which is the breakdown voltage, so neither of them is breakdown. Okay, that's good. So we need two information now that they look like reverse and they look like also not in breakdown. So let's make an assumption. Let's assume this is assumptions that we're gonna prove right or wrong. If it's wrong, we're gonna prove another one. Let's assume that. So based on this two information, we are working in that area here, from the start to here, before the breakdown. So let's assume that D2, for example, is in deep reverse, and D1 is also in deep reverse. So this is our first assumption that we're gonna prove right or wrong. If D2 in deep reverse, that means ID2 should be equal to minus I naught 2 minus 2 microamps. If D1 is in deep reverse, so ID1 should be minus I naught 1 should be minus 1 microamps. Is that right? What I just write here can be right? No. Basically, because we know that ID1 should be equal to ID2 because they are in series. So this assumption is wrong. So assumption 1 is incorrect. Let's mark it there. Okay. So let's have another assumption. Let's assume that D1 is in deep reverse but D2 is not. What does that mean? If I assume that D1 in deep reverse, that means I'm working in here, in that region here. And the ID1 is equal to minus I naught 1. If D2 is not, that means D2 is working in that area here. That means I D1 as a magnitude is less than I naught, I'm sorry, 2 as a magnitude. Or I naught 2, because it's positive. And let's see if this is right or wrong. Okay. So if I now we're gonna just continue, and if everything looks okay, if every number we are expecting is okay, and I will say what is the checks that we're gonna do to check that, then this will be a correct assumption. Okay, so let's do that. So ID2 is equal to minus I naught 1. I'm sorry, D1. So D1 is in deep reverse, so ID1 is equal to minus I naught 1. Okay, we know one of the unknowns now. And since ID1 equal to ID2 because the two diodes are in series, so ID2 is also become known now. It's equal minus I naught 1. Minus 1 microamperes. Can we calculate VD2, for example? Yes, we can do that because ID2 is equal to I naught 2 exponential VD2 over VT minus 1. ID2 we just calculated minus 1 microamps. I naught 2 is known. I naught 2 is 2 microamps. Exponential VD2 and VT is 0.26 minus 1. So this is one equation and one unknown, right? So from that we can calculate VD2. It will be minus 18 millivolt, I believe. Where is it? Yes, 18 millivolts. Now we're gonna ask ourselves a question. Is that seems right or wrong? That seems right because simply, if we say that diode 2 is not in deep reverse, it should be working in that area here. Okay. The diode turn into deep reverse if VD is much larger than VT. Okay, VD as a magnitude because it should be negative in reverse. But here, if we compare, VD2 is minus 18 millivolt, while VT is 26 millivolts. So this is less than VT. So that value here looks good, looks correct, because that will not turn the diode into deep reverse. One last thing to do is to calculate VD1, and we can do that using KVL. So through KVL, V input plus VD1 plus VD2 is equal to 0. So from this, we know V input it's 90 volt. We know VD2 now it's minus 18 millivolt. Okay, so we can calculate VD1, and it will be minus 89.98 volts. Now, before we say that this assumption was correct or wrong, let's evaluate ourselves using the information that we know and what we was expecting. These are the numbers that we got. We got 4 numbers. We got ID1 equal to minus I naught 1 minus 1 microamps. We got VD1 equal to minus 89.98 volts. We got I naught 2 equal to ID1, ID2 equal to also minus 1 amps. we got VD2 equal to 18 minus 18 millivolt. Let's now make some checks to know if this is right or wrong. First, we are working in reverse bias, right? Working in reverse means the voltages must be negative. And we have VD1 negative and VD2 is negative, so that looks okay. We said that D1 in deep reverse, so ID1 is 1 micro, that's correct. We said that D2 is not in deep reverse, so its current as a magnitude should be less than I naught. So this is as a magnitude will be 1, ID2 as a magnitude is 1 microamps. This is less than I naught 2, which is 2 microamps. This is also correct. So we also assumed that D1 is reverse but not breakdown. And if we look here, the breakdown voltage is 100 volt, but here VD1 as a magnitude, which is 89, is less than the V breakdown, which is 100. So all the numbers that we got is actually good. And we have one last check also that we can do. Since we are in deep reverse for D1, okay, if you apply ID1 equal to I naught 1 e to the power VD2, VD1, I'm sorry, VT minus 1, you should get minus I naught 1. And you will get that. Why? Because VD now is minus 89 volt, which is as a magnitude much, much larger than VT, which is 26 millivolt. Okay, it's 1,000 times, more than 1,000 times bigger. So it's like e to the power minus infinity, and e to the power minus infinity is actually 0. So ID1 will be equal to minus I naught 1. So based on all these checks, okay, without solving any equations graphically or iteratively in Matlab or whatever, just by a paper and a pen, we could get the solution, and this actually a correct assumption. So assumption 2 is correct based on these checks here. One may say, why we didn't assume the opposite? That D1 is in, D2 is in deep reverse and D1 is not in deep reverse. We can do that, and we can disprove that as well. Because now we know the solution, by the way. So any other assumption should be wrong, okay? And I will leave that to you because of the time. So in your homework, okay, I will publish it after the lecture. You must disprove that if we start by D2 is deep reverse and D1 is not in deep reverse, then this will be an incorrect assumption, okay? One last, you know, let's drop that, these numbers here, let's drop them on our graphs here, just to have more visualization, okay? So the solution that we got is that VD1 is equal to minus 89.9, which is something here, minus 89.9. It's before the breakdown, so there is no breakdown. And the ID1 is minus I naught 1, which is a corresponding value for this, minus I naught 1. And for VD2, the current was minus I naught 1, which is half the way to minus I naught 2, something in here. And the voltage was very small, okay, minus 18 millivolt. Okay, so we are not in deep reverse. Okay. Any solution, guys? I'm sorry. Any question, guys? Anything not clear? I know this is the first time to see something like this. Okay. But believe me, if you just do it by your hand and try many assumptions, the correct assumption. Any other assumption should be incorrect. Okay. So let's now do
Wait,
the last. Yes.
I do. When you said in deep reverse, you mean like as in the diodes are actually reversed?
So deep reverse means, let me write it here. Deep reverse in different color means and not breakdown. Deep reverse and not breakdown. Okay. So deep reverse means with that and not breakdown, that V diode should be negative. V diode as a magnitude should be less than V breakdown. Okay. And I diode should be minus I naught. That's what I meant by deep reverse. And if we locate this, this region on the characteristics, this should be the region. From that point to that point. All the regions that have constant current, which is minus I naught.
Okay, so when you're looking for deep reverse, you're looking at the graph rather than the circuit.
Look, I know, yes, I'm looking at the graph, okay, but remember the graph reflects the characteristic of one of the elements on the circuit.
Oh, okay, yeah.
Okay, so they are connected. It's just like if I look at the graph of the Ohm's law of a resistor, but the resistor is still in the circuit. Okay.
Yeah.
So that graph here will control the operation of the diode in the circuit. Just like Ohm's law controls the operation of the resistor, its voltage and its current in the circuit. Okay?
Okay, that makes more sense. Thank you.
Now, let's do B. So in B, the input now becomes 110 volts. Okay, 110 volts. What we end up from A is that let's summarize this. At the input equal to 90 volts, V diode 1 was equal to minus 89.9 volt. ID1 was minus I naught 1. VD2 was very small, okay, minus 80 millivolts. And the ID2 was minus I naught 1 as well. Okay. Now we increase the voltage, the input voltage to 110. And remember, V breakdown is equal to 100, or as absolute. If it's just, without absolute, it's minus 100. We see that now this V input is larger than the breakdown voltage. Okay. So, but we are not sure. Yes, this is larger than the breakdown voltage. So maybe one of our diodes can reach the breakdown and become a breakdown diode, or maybe not. For example, we increase this voltage by 20 volt because it was 90 and it become 110. Okay. Maybe this all the increase or all the increment in the input voltage goes to diode 2, and diode 2 was 80 millivolt, minus 80 millivolt, it become minus 20.018 volt, maybe. And if that happens, D1 will be the same at the same voltage, which is minus 89 volt, and will not be in a breakdown. That's why it's important to put the data that we got at 90 here in number B, because it will lead us fastly to the correct assumption. So without assuming many assumptions that is incorrect, and at the end go to the correct assumption, we can assume it in the beginning. I will do also two assumptions, one which is the correct one and one which is, you know, incorrect, and we will disprove it. Okay, now let's be smart and look at, you know, what we get here in A. So the last thing that we reached here, yeah, we found that D1 is at minus 89, just 10 volts away from the breakdown. This is around 10 volts. But this guy, D2, is, you know, it's just 18 millivolt. It's very far away from the breakdown. So when we increase the input voltage by 20 volt, it's maybe probably, or I'm sorry, it's probably that this will turn diode 1 into breakdown, okay? And if we are a breakdown, we have some information, then we can solve the circuit very fast. And this is actually the correct assumption. So let's do it. Let's do it. So assume since at the input was equal to 90 volt, VD1 was minus 89.9, just 10 volts away from VBD. At the same time, VD2 was equal to minus 18 millivolt, which is approximately 100 volt away from the breakdown. So assume D1 in breakdown, and as usual, D2 just in reverse. And let's see what will happen. And we'll prove that is correct. And then I will assume another assumption after finishing the correct one to show you that other assumptions will be incorrect and how you can disprove them. So let's do that. If D1 is in breakdown, then basically VD1 is equal to minus VBD, which is minus 100. We know one of the unknowns now. And we know another information about diode 1. Since it's in the breakdown, ID1 as a magnitude should be larger than I naught 1. Because if we go back here in breakdown, so the current just exceeds I naught in negative. For example, become minus 2 I naught, minus 3 I naught, whatever. Something larger than in magnitude I naught. And of course must be negative, because we are still in the reverse bias. But now in breakdown, we go to the breakdown. So reverse and the breakdown. So from KVL, we know the input plus VD1 plus VD2 equal to 0. Basically, from here we can know VD2 because V input is known 110, VD1 is known minus 100. So this will be minus 10 volt. This is deep reverse. So now diode 2 based on that assumption, diode 1 based on that assumption goes to the breakdown, and diode 2 goes to the deep reverse. And in deep reverse, ID2 should be equal to minus I naught 2. And we can do it again using the equation. You can do that in that way. ID2 equal to minus, I naught 2 exponential VD2 over 26 millivolt minus 1. If you do it, the calculator will just give you minus I naught. Okay? So now we get yes, and we know that ID1 is equal to ID2 because they are in series. So ID2, or I'm sorry, ID1 is equal again to minus I naught 2. Now we get 4 numbers. And now we need to check if the assumption is correct or wrong based on these 4 numbers. So let's write this in another color. So ID1 equal to minus I naught 2. We know we are in breakdown, so we know the conditions that ID1 should be bigger than or greater than I naught 1 as a magnitude. I naught 2 is 2 microamps, which is as a magnitude larger than I naught 1, which is 1 microamps. So this is correct. And VD2, we discover it is in where VD2? Yeah, it's minus 10. Which means deep reverse. And by the equation here, we find that ID2 is equal to minus I naught 2. And we know if a diode is in deep reverse, it should have a current equal to minus I naught 2. Or minus I naught, whatever the diode is. Or whatever the I naught is. Okay, so it looks like this is a correct assumption. Because it gave us, you know, reasonable numbers. It may be weird that such kind of solving, you know, circuits with diodes, but believe me, this is, you know, the most fast way that, you know, everybody's using. This is a formal ways, and we do that a lot. We will give assumption, you know, follow the assumption, we prove it, disprove it, okay, just by looking at the numbers. For example, we are saying it's in reverse, right? In reverse, you cannot get positive numbers for the current. If you get current with positive, then the assumption is incorrect. And you can do that by yourself, by the way. You can assume in the beginning, in this specific example, although you know it's reverse, you can assume it's forward. Then you will find that the numbers are negative. So it's not forward, it's reverse. Now let's assume another assumption. So we just complete the example. But I will just give you a hint how to, you know, if you assume another assumption rather than this in number B, okay, when the V is 110, how to disprove it or how to see if it's correct or wrong. So let's assume an incorrect assumption. So we just finished, guys. So this is the solution. It's finished. It is just a hint. Let's assume that we are still, that this increase, you know, in the V input does not, you know, lead diode 1 to breakdown. Okay. Let me see where I put that. Yeah. Let's assume the opposite. Let's assume D2 is in breakdown, okay, and D1 just, you know, just in deep reverse. This is wrong, and I will show you how it's wrong. Okay, so if D2 is in breakdown, then VD2 is equal to minus 100. Good. And the ID2 should be, as a magnitude, larger than I naught 2. Good. We assumed also that D1 is in deep reverse, right? So deep reverse means that ID1 is equal to minus I naught 1 and not breakdown. So we assume D2 go to the breakdown and D1 does not broke down. So that means if D1 is in just in deep reverse, so ID1 should be minus I naught 1, which is 1 microamps. Simply, that's incorrect because ID2 should be larger than I naught 2. and you know ID1 is equal to ID2. So ID2 will be equal to -1 microamps. And this is less than, as a magnitude, is less than 2 microamps. So this assumption is incorrect. This is wrong. Just for very simple analysis. Okay? You guys are following?
Yeah, we're following.
Good. So this is how to deal with such, such problems. Okay? Even with exact, now we get exact solutions, by the way. So these are the solutions that you would get from, solving the equations together. Okay? But, in a smarter, way, just by looking at the data that you have, okay, try to assume some, some reasonable assumptions, so that and then after getting the numbers, just look at the numbers and see if they are right or wrong, if they are violating the assumptions that you assumed or not. Okay. Okay, guys, just finish. Okay, next time we'll take more and more examples. Okay, and we're gonna look at other ways, to deal with the diode. Okay, some approximate, models for it, so that we're gonna make it a lot easier than this. So now we are avoiding, with this example, we avoid the equation, solving the equations together, and we still, could solve the examples in just paper and hand. Okay, and next lecture we see some models, approximate models, that will make that even easier than this. Okay, so any questions so far? Any concern?
Could you really quickly repeat again why this one is not right?
Good, that's good. So we're gonna assume that D2 is in breakdown. That means D2 should have a voltage of minus VDD. And since this is I naught 2, the current here as a magnitude should be larger than I naught 2, right? That's clear?
Yeah.
Okay. So I assumed that, so this is V22, this is ID2. I assume that D2 is breakdown, just opposite to the first assumption that was correct. And D1 just in deep reverse. D1 in deep reverse.
Yeah.
Deep reverse means that our diode and not breakdown is working in here. After this point and before this point. So the current should be minus I naught 1, and the voltage should be one of those values here. Okay, any one of them. This is VD1, ID1. Okay. Since we assume that V2 is breakdown, then for all these values here of the current, 1 voltage. It's constant voltage. VD2 is minus 100. And we know for sure that ID2 should be, if this is correct, ID2 as a magnitude should be larger than ID2. Now we assumed also that D1 is in deep reverse. So its current should be saturated at minus I naught 1. So ID1 equal to minus I naught 1 equal to minus 1 microamps.
Yeah.
But we know from the circuit that because they are in series, ID1 equal to ID2 because they are in series. So ID2 is equal to minus 1 microamperes, right?
Yeah.
But we said that ID2 should have a current and a magnitude larger than its I naught, and its I naught is 2 microamps.
Okay.
So this is ID2 is 2 microamps. So how come these values they should be more than 2 microamps? It's just one of them is 1 microamps. So how come that doesn't that's the violation? This value here is less than 2 microamps as a magnitude. That's why we are not here.
Okay.
Let's have in just 1 minute. Let's have another incorrect assumption. Now let's assume that D1 and D2 are both breakdown.
Yeah.
Okay, so this is the circuit here. Here 110, VD2, and VD1. This is also incorrect, but let's see how. If we assume that D1 and D2 are both breakdown, then VD1 is equal to minus 100, VD2 is equal to minus 100, right? So you have
Yeah.
here minus 100 and minus 100. Now let's see what will Kirchhoff voltage law will give us. So Kirchhoff voltage law is saying that 110 plus minus 100 plus minus 100. This is how much? This is minus 90. That's not equal to 0. So this is also incorrect assumption.
Oh, okay.
Right? So that's the game. You know, you can go blindly and assume anything. You can start by this one in the last that I just mentioned, that both of them are breakdown. Okay, but how come? Because the input voltage itself cannot give each one of them 100. So if both of them break down, this should be 200. The input should be at least 200, right? So that's the game. You assume, get some numbers, and try to verify if your assumption is correct or wrong.
Okay. All right, that makes more sense. Thank you. Thank you.
Thank you very much. See you next week. Thank you very much.